Okay, so we're going to start on topic 12. So topic 12 is going over the property of matrices. So we're going to go over what is a matrix, and then we're going to just talk about some of the basic operations of matrices. So for what is a matrix, we have four vocabulary here. The first says coefficient matrix. A coefficient matrix is a rectangular arrangement of numbers in rows and columns. These numbers consist of the coefficient of the variables in a set of linear equations. So all that means is that we can take a linear equation and we can turn it into a matrix. Just like if we have a matrix, we can turn that into a system of linear equations. Then we have a constant matrix. That's a matrix where all numbers are constant. So this is where we would not be able to turn it into that system of linear equations because everything inside of a constant matrix would just be a number, not anything attached to a variable. Then we have the elements. So the elements are the numbers inside the matrix. And the dimensions is the size of a matrix defined by the number of rows and columns. So the first thing we're going to look at is just how to identify the dimensions of each matrix. When we are looking at the dimensions, we always look at rows, then columns. So for example, in this first one, we're looking at how many rows there are. So in this case, there are 4 rows. See, 1, 2, 3, 4. Okay. Then we look at the columns. So in this case, how many columns? 3. So this is a 4 by 3 matrix. And that's all we're doing for these examples is just identifying the dimensions.
So the numbers don't really matter here?
No, not yet.
Okay.
So the reason we have to learn to identify the dimensions first is when we are doing the operations of matrices, there are special cases where you can only add or subtract matrices that have the same dimensions. Okay. So looking at number 2, what are the dimensions? What's the rows and what's the columns? Good, this is a 2 by 4 because if we look down the rows, there's 2 rows. And we look across the columns, there's 4 columns. So that is a 2 by 4 matrix. Okay, what about number 3?
1 by 1? No, 3 by 1?
3 by 1, because if we look down the rows, there's 3. Across the columns, there's 1. So this is a 3 by 1 matrix. And then last example, what is the dimensions of 4? 3 by 3. So looking at rows and columns, we see that this is a 3 by 3 matrix. And since our columns and rows match in this matrix, this is called a square matrix. And just think if we looked at the dimensions of a square, all the sides would be the same. So just like this matrix here. Okay, like I said earlier, we can turn systems of linear equations into augmented matrices. So an augmented matrix is a matrix used to solve linear equations. It's a combination of a coefficient matrix and a constant matrix. So the only thing you need to know about the augmented matrix, if we look down at the, not the examples yet, the only difference is that your matrix is going to have a line right here. So we'll have a bunch of numbers here, a number here, and the line down the middle. That line just represents an equal sign. Okay. So in these next examples, we are going to write the following as either a system of equations or a matrix. So whatever we see, we're going to do the opposite. So for number 5, the first thing we have to do is we have to look at all the coefficients in front of our variables. So looking at the first equation, what's the coefficient in front of x? 5. What about in front of y? -2. And then what is this equal to? -6. We're going to do the same for the other equation. What's the coefficient in front of x? Good. Remember, if we don't see a number, we assume it's 1. So this is a -1. What about in front of the y? 5. And then what is this equal to? 15. So since we have 2 x's and 2 y's, the coefficient matrix that's going to come first is going to be a 2 by 2. So we're going to draw that. So we just write our matrices bar, and then the top 2 numbers are the coefficients in front of the first equation. So we said that's 5 and -2. And then the second set of numbers are the coefficients in front of the second equation. So -1 and 5. And then remember I said we draw this line because that represents an equal sign. And then we write the numbers that each equation was equal to. So -6 and 15. And then we close our matrix. So when we go back up to the definitions, this is what I was talking about as a coefficient matrix. Because it's the numbers that are attached to those variables. And then a constant matrix. Just a number that they are equal to. Which means this whole thing is called an augmented matrix.
So was that it?
Yeah, that's the answer for 5.
Oh. Yeah. There's no way.
We're not solving the matrices yet. That will be next one. That's where it gets a little complicated. This one, we're just setting them up in these notes. Okay, so looking at 6, we got to do the same thing. We're going to have to label all of our coefficients. So what are the coefficients in the first equation? Good, -3, -4, and then equal to 20. What about the second equation? Good. And then 25. The only thing here is you just have to remember to keep the negatives. Okay, so I start my matrix. I write the first 2 numbers in front of my x and y, so -3, -4. I write my numbers in front of x and y in the second equation, so 3 and -5. Draw my equal sign bar, and then what each of them are equal to. And that's my answer. So if you were to find the dimensions of this matrix, you always find the dimensions of the coefficient matrix, not what it's equal to. So this is technically a 2 by 2 matrix because we have 2 variables in 2 equations. Just think of it that way. 2 variables, 2 equations. That's why it's a 2 by 2. Okay. We don't use those numbers after that equal sign bar until we're solving. Okay. So let's look at number 7. So what's different about number 7? Good, we have one more variable, which means we have a third equation. That just means we're going to have a third row when we're adding our numbers into the matrix. So first I find all my coefficients. So what about the first equation? What's my coefficients? Good, 1, because I don't see anything in front of z. What about the second equation? Good, -2, -1. And then the last equation? Good, 4, 1, 4. So I'm going to take all those numbers we just said and we're going to put it in our matrix. So we said 4, 3, 1. That's the first equation. 3, -2, -1. That's the second equation. And then 4, 1, 4. That's the last equation. Then I write my equal sign bar and I write all the numbers that each equation is equal to. So -13, -19, -25. Close my matrix. So in this case, what's the dimensions of this matrix? 3 by 3. So we only pay attention to the matrix in front of that bar. So this is a 3 by 3 matrix.
So it's a square matrix.
Correct. All of these that we're working with when we're solving are going to be square matrices.
Oh, I thought it was only when it was 3 by 3, sorry.
Oh no, like this last one on number 6, this is a square matrix too because it's a 2 by 2. They're the same number. As long as they're the same number, they're a square matrix. Okay. Okay, what do we notice about number 8?
No y.
There's no y. So what do you think we would put in place of a y?
0.
A 0. So let me go ahead and start highlighting my coefficients. So I have -2 and -4. In front of my x is a -1. And we said our y, since there isn't a y, is going to have the coefficient of 0. Okay. So if I was to write my matrices, it would be -2, -4. What would be the second line?
1, 0.
0. And then equals 2. What are my two numbers? Good. And that would be my answer. So with matrices, if we are missing a variable, we have to have that placeholder of a 0. Because it would not make sense to not have a number here, because then it wouldn't be a complete matrix. If we have x and y variables in each equation, that means this second line also has to have x and y variables. Okay. Okay, now we're looking at the opposite. So now we're looking at a matrix that we have to write into a system of linear equations. So all we need to remember here is what our columns were. So this first column, remember, was our x variable. The second column here was our y variable. And that last column, it's what it's equal to. So these are the coefficients that go in front of each of the variables. So that means our first equation would be 3x plus 4y equals 1. I took the 3, put it in front of the x, the 4, put it in front of the y, equals 1. Put that at the end. So knowing that, what would be our second equation? Good, -3x plus 2y is equal to 23. Those two equations are our answer. We're just turning it from matrix now to system of linear equations. Okay. Okay, go ahead and take a moment and try 10. Just remember this is x, y, and then whatever it's equal to. Okay, so you should have got -5x plus y, because we don't need to write 1y, is equal to negative 16. And then x plus 5y is equal to negative 2. You could place the ones there if you wanted, but the correct way would just to be without the ones, just the variable. Okay. Let's look at number 11. So in number 11, we have a whole other column. So what do you think this last column is labeled as? Let's say we have x, y, z. And then our equals 2. So these equations are going to have 3 variables. And we're going to have 3 equations this time. So we would have 3x minus 2y plus 4z equals 6. Taking all the numbers in that first row, placing them as coefficients in front of our x, y, and z variables. Okay. So then for the next one, you should get 9x plus 4y minus z equals 0. Okay, I don't need to put minus 1z. Minus z is the same. And lastly, you have 6x minus 8y minus 3z is equal to 3. And if they don't give you the variables to use when you're turning them in from matrix to system of equations, the variables that are typically used are x, y, and z. Of course, in this case, they didn't give us any option in any of these examples, so we could have used A, B, and C, as long as you're using 3 different variables to represent them. Okay, and then last one for this example is number 12. So again, we still only have that 2 by 2 matrix, so it means I'm only using 2 variables, x and y. These are the coefficients going in front of the variables. And then whatever after that bar is the equals. So I have x minus 2y equals negative 1. And negative x plus 3y equals 3. So again, we were just turning matrices into systems of linear equations, or the opposite, turning systems of linear equations into matrices. Any questions on that?
For the test, if we were to put a 1 in front of the variable, would be marked wrong, or?
It wouldn't be marked wrong, but it's just best to do to leave the 1 out, because that's what's going to help you in later math courses. But I wouldn't mark it wrong. If you put 1x, that's fine. The purpose of doing, well, like just these examples? Because in next notes, we're going to solve using matrices. So you have
like a purpose of nature, like this whole thing.
Oh, this is just another way to solve system of linear equations. So remember, we learned how to graph them, we learned substitution, we learned elimination, and now we're learning the last method, which is matrices. Okay, so continuing on to the last concept, which is operations of matrices. So the only operations we're going to discuss in this course is addition, subtraction, and scalar multiplication. There are plenty of other operations, such as multiplying 2 matrices, dividing 2 matrices. All of that is for a different course. So for adding and subtracting matrices, we have to make sure that the 2 matrices that we're adding and subtracting have the same dimensions. If it does not have the same dimensions, then our answer is undefined. Okay? And then with scalar multiplication, it doesn't matter. When we see scalar multiplication, we're going to think of distributing, because there's just going to be one number outside of the matrix, and we're just going to have to distribute that inside the matrix. Okay. So number 13, our first step is to identify the dimensions of each one. So what's the dimensions of the first one? 2 by 1. What about the second one? 2 by 1. Okay. Since they are both 2 by 1 matrices, that means we're able to subtract them. When we subtract them, we're going to get an answer that is also a 2 by 1 matrix. So all we do is we subtract the numbers that are in the same rows. So for example, and let me erase this part so I can write it out step by step. So in the first one, we have -4 minus 1. And then we have -2 minus a -3. Okay? This is me writing it out step by step. So all I did was subtract across. So if I simplify this, -4 minus 1 is -5. What happens when we minus a negative? Turns into a positive, so -2 plus 3 is 1. Meaning our answer for this is -5, 1, which is a 2 by 1 matrix. Okay. It has to match the 2 that you are adding and subtracting. If you end up with like a 3 by 2 matrix, then you did something wrong. So let's look at 14. Our first step is to do the dimensions. So what's the dimension of the first one? 1 by 2. What about the second one? Same thing. So are we able to subtract? Yes, so we are subtracting the 2 first terms, so right here, and then subtracting the 2 second terms. Okay, so we have -2 minus a -2, and then 1 minus a -5. We know that minus a negative in both these cases is plus a positive. So that means we have -2 plus 2, which is 0, and 1 plus 5, which is 6. Okay, this is our answer because we still have a 1 by 2 matrix. So the only important thing is to make sure we are adding or subtracting the correct element inside of the matrix. Okay. Okay, number 15. Again, our first step is to identify the dimensions. Are these the same? Yes, they're both 1 by 3s. 1 by 3s. So when I subtract both of these, I'm subtracting it by the corresponding element. So I'm going to do -3 minus what number? -2. And then I'm going to do -5 minus -3. And -1 minus 1. Simplifying this, I know that plus or minus a negative is plus a positive. Oh. So -3 plus 2 is -1. -5 plus 3 is -2. And -1 minus 1 is what? This is why I asked. No, it's not 0. -2. That was a common mistake on test 1. It's just you guys were adding wrong. Adding or subtracting wrong. Yep, -1 and a -1 becomes a -2. Again, we know we did this correctly because this is a 1 by 3 matrix, and this is our answer. Okay, any questions so far? Okay. Let's look at number 16. So now we're adding matrices, okay? So same concept, we're just adding them. First, we have to check if these have the same dimensions. Yes or no? Good, they do have the same dimensions. What are the dimensions? 3 by 2. So it's 3 by 2, 3 by 2, which means our answer is also going to be a what? 3 by 2. Okay. So we add all the corresponding numbers. So that means this one with this one, this one with this one, this one with this one, so on and so forth. Okay, all the corresponding numbers. So we have -6 plus -4, -6 plus -1, -6 plus 5. That was the first column. Now we're looking at the second column. -3 plus -2, 4 plus 4, and 5 plus 3. Okay. Simplifying this, -6 and -4 gives us -10. -6 and -1 gives us -7. -6 and 5 gives us -1. It's the first column. And then -3 and -2 gives us -5. 4 and 4 gives us 8. And 5 and 3 also gives us 8. Okay. So again, this is a 3 by 2 matrix. And that's our answer. Okay. Let's look at number 17. Do we have the same dimensions?
Yes.
Yes, so that means we can subtract. So we have -3 minus 3, 1 minus a -1, 4 minus a -2, and 3 minus a -3. Subtracting all of the corresponding numbers. Then I'm going to go through here because I know that minus a negative is plus a positive. And then simplifying this, -3 and -3 gives us -6. 1 plus 1, 2. 4 plus 2, 6. 3 plus 3, 6. So that means this is our answer, which matches the matrix C of a 1 by 4. Everyone see where? Got those? Okay. Okay, number 18. First step is to check if the dimensions are the same. Are they the same? Yep. More often than not, they will be the same. So then adding these matrices, I have 2 plus -4, -2 plus -1, -1 plus -4, and 1 plus -5. Again, I'm adding the corresponding numbers. Okay. Then to simplify this, 2 and -4 gives me -2. -1 and -2 gives me -3. -1 and -4 gives me -5. 1 and -5 gives me -4. So this is my answer, which matches my 1x4 matrices at the top. Okay. Let's go ahead and skip to 21. Okay, first step is to do what?
Dimensions.
The dimensions. Are these dimensions the same? Yes, they are the same. We have a 2x2 square matrix. So that means when we add these together, we're also going to get a 2x2. So again, we're adding all the corresponding numbers. So from -1, we would add 5. For -2, we would add 3. 6, add 5. 4, add 6. All the corresponding numbers. So I'm going to go ahead and write that out. So -1 plus 5, -2 plus 3, 6 plus 5, 4 plus 6. So simplifying that, I get 4, 1, 11, and 10, which is also a 2x2 matrix, and my answer. Okay. Now let's look at 22. Are these dimensions the same?
No. Yeah. No.
They're not. So let's go ahead and first label the dimensions. So what's the dimensions of the first one?
2x3.
Yep, so looking at row and column, this is a 2x3. And what about the second one? Good, 4x1. So row and column, 4x1. These have to match in order to add or subtract. So since they don't match, we would consider this to be undefined. And that's all you would show me for your work, is that you labeled the dimensions of each. You notice that they are different, so we cannot subtract, so it's undefined. Okay, let's look at 23. 23 is an example of scalar multiplication. So in this case, we just have a number outside of our matrix. So when you see this, I want you to just treat it like it is a distributing problem. So we would distribute that -4 inside of the matrix, and then this is just going to scale that matrix into a new matrix. So this would be -4 times 1, -4 times 5, and -4 times 2. So when we simplify that, that's -4, -20, -8. And that would be our answer. So when we see scalar multiplication, it's the same as just seeing a number outside of the matrix. So we would distribute that number in. Okay. Go ahead and try number 25. So again, this is scalar multiplication, so that means we have to give that 4 to everything inside of the matrix. Give you guys a few seconds to do that. Okay. So what you should be doing is you should be distributing that 4 to the top row and to the bottom row. Which means 4 is being multiplied by all of those numbers. So you should have got negative 20, 12, negative 24, negative 12, 4, negative 12. So notice this is still a 2 by 3 matrix. The only difference is that it scaled this matrix 4 times, so it made it 4 times larger. Okay. Okay, and then the last one we're going to look at is number 30. So again, try this one on your own and get an answer. So you should be checking the dimensions first before trying to add. So you should have got the first matrix to be a 1 by 3, and the second matrix to be a 3 by 2, which tells us our answer is what? Undefined.